Okay, here we go. Section 2.1, page 59 in the book. They always have these kind of cool questions, real life type questions where you might use calculus at the beginning of the chapter. And this one's kind of interesting. It's called an economic injury level. It's a very important thing around here with all the agriculture we have. So let's just read about it real quick. An economic injury level, EIL, is a measurement of the fewest number of insect pests that will cause economic damage to a crop or a forest. It has been estimated that monitoring pest populations and establishing EILs can reduce pesticide use by 30 to 50%. So we allow a few organisms to survive without killing everything off. And if we do that, we don't suffer any economic damage from the sale of our crop, but we also don't have to use so many pesticides if we allow a few and try to control that. Accurate population estimates are crucial for determining EILs. A population density of one insect pest can be approximated by this a particular species of insect, t squared over 90 plus t over 3. Do you recognize that thing that you're looking at as a polynomial? Because it's really 1/90th t squared plus 1/3 t. That's a polynomial. It's just got coefficients of fractions. Just so you know, it's just a polynomial. And this is what it said. It can be estimated this way as pests per plant, where t is the number of days since initial infestation. What is the rate of change of this population density when the population density is equal to the EIL of 20 pests per plant? Section 2.4 will help you answer this question. In other words, we want to know how fast are they growing when the EIL, the D of t, is 20. How fast are they growing? That's a typical question you ask in calculus, and it's a pretty powerful thing to be able to answer. Anyway, we won't be able to answer that until we get to section 2.4, so you just have to hold off on that. Maybe we'll take a look at this again. What's that? What'd you say?
Nothing.
Oh, okay.
Unnecessary comment.
All right. I always like what the author says at the beginning of the chapter. He says what I want to say in a much more concise and intelligent sounding manner. So we're going to read it together. Okay? We're not going to read the entire textbook, but we're going to read these blurbs at the beginning because it helps you understand what's coming up. The concept of a limit is one of the ideas that distinguishes calculus from algebra and trig. One of the ideas. There are three. The limit, the derivative, and the integral. This chapter is about the limit. Okay. In this chapter, we show how to define and calculate limits of function values. The calculation rules are straightforward, and most of the limits we need can be found by substitution, graphical investigation, numerical approximation, algebra, or some combination of these. Now, I want to talk to you about what each of those means. Substitution means to plug something in. Graphical investigation means let's take a look at the graph and see how it behaves at certain x values. Numerical approximation is when we look at the table aspect of your graph, where you have a list of x's on the left and y's on the right. You look at specific points listed as numbers. That's numerical approximations. Algebra, you know what that is, straightforward pencil, paper figuring things out, or some combination. Notice the title of your book, Calculus. Graphical, numerical, algebraic. We will not study all three of these every time we talk about something. We will pick one or two methods to study that seems the most appropriate. You'll see it very clearly today already, right in example 2. You'll see that we're going to use different kinds of things to investigate. Okay, so you're going to have to be really, really comfortable with your calculator very soon. One of the uses of limits is to test functions for continuity. Continuity. That's an extremely important concept. Continuous functions arise frequently in scientific work because they model such an enormous range of natural behavior. You'll see what that means. Continuity and continuousness is extremely important in this. We'll talk about it. They also have special mathematical properties that are not otherwise guaranteed. Continuous functions do. Okay? I want to read you something out of a book that I absolutely love, but it won't mean much to you, and it would be a good idea for you to read this after You'll finish calculus. This guy's name's Berlinski. You'll let me refer to him a lot. Berlinski says this or whatever. It's called a tour of the calculus. Berlinski. Okay. And this is what he says as he describes calculus. I like Berlinski because instead of being a bland, two-dimensional, on whiteboard kind of a subject, he brings it to life. I'm not kidding you. He takes you all around the world and not just shows you where calculus is useful. He makes talking about the calculus feel like a real-world thing. I mean, he really does. It's very cool. This is what he says. The frame of the book. I like this. It's just this long, so just hang in there. The overall structure of the calculus is simple. It is. It's the algebra that'll kill you in calculus, not the concepts. Concepts are beautiful and easy and simple. Making them work in algebraic situations, that's what kills you. The overall structure of the calculus is simple. The subject is defined by a fantastic leading idea. One basic axiom means something we accept without proof. A calm and profound intellectual invention. Grab a book. Grab a book, Sonny. A deep property. Two crucial definitions. An ancillary definition. A major theorem. And the fundamental theorem of calculus. That may seem like a lot. It is kind of a lot. But it can all be summarized in that thing. Here it is. The fantastic leading idea is that the real world may be understood in terms of the real numbers. Put things on a number line. So we won't be discussing imaginary numbers in here. Only the reals. The calm and profound invention is the mathematical function. That's all we will study in here, are functions. Now you're going to study other things that are not functions when you like ellipses and circles and hyperbolas and stuff like that are not functions. You'll study those in subsequent courses in calculus, but your introduction to calculus here, only functions. There's a basic axiom, something we accept without proof, and that axiom brings the real numbers into existence. We don't have to worry about that. We all believe they exist. It's good. A deep property, continuity. I told you it was important. Deep property, continuousness. Crucial definitions, instantaneous speed and the area underneath the curve. They don't seem very much related, but they're very related. It's very cool when we get to that. Instantaneous speed and the area under a curve between the x-axis and the boundary of a curve is very important. The ancillary definition, the limit. So we're going to be studying this chapter. Major theorem, the mean value theorem. That is such an important theorem that you may call it the MVT, and everybody knows what you're talking about if you're studying calculus. Mean value theorem. Luckily, it's not too hard to understand. And the fundamental theorem of calculus. And he says, which is the fundamental theorem of calculus. And it's nothing more can be said about that. It is the absolute basis. It's a very, very cool theorem. Hopefully you'll have the same epiphany I had when I discovered it. It was amazing. Anyway, these are the massive load-bearing walls and buttresses of the subject. You'll come to be very familiar with all of those things as we go along. So we got to begin somewhere. Here we go. Rates of change and limits. What's another word for rates of change when we're talking about math? There you go, guys. I'm glad you got that. That's great. Just to propose something that might already throw you off a little bit, if you were going to travel from here to Rexburg, and then you picked up something and came home, not Rexburg, from here to Idaho Falls, say Rexburg, Idaho Falls. Let's say it's 30 miles so that it's easy to think about, okay? You travel 30 miles out of Falls to pick something up, and you're going to pick it up on a trailer, and when you come home, you have to go a lot slower because your load's really heavy and you have to be careful, okay? So let's say that you went down to Idaho Falls traveling a constant rate of 60 miles an hour. I know. Like me, I'm old. My old jitney car that won't go faster now. My motorcycle, which only goes 50. Anyway. So 60 miles an hour, constant rate of speed. You go down, you pick it up, and the time you're there doesn't count. Just when you're on the road. And it's a constant 60 going down. And I know it's really slow, but we need to do this to calculate in our heads. Constant 30 coming back. What's your average rate of speed? That's what everybody thinks, but it's not true.
Wait. just.
Went down going 60, came back going 30, average rate of speed.
40 negative, because it took you twice as long to do 30, so you have to count it twice.
Okay, and that's an excellent idea, but it's still not 40. But still, you're thinking along the right lines. But it's not 45. You can't find an average velocity by averaging the velocities.
It's an hour and a half total.
Is this one?
And
that's 60 miles, so.
yeah, hang on, you're getting there. But the reason why you can't, folks, is because you spend more time going 30.
Yeah.
So it will be less than 45 miles an hour. Because time is an element. Average speed is the distance that you traveled divided by the time you spent traveling it. What distance did you travel in this scenario? 60 miles. How long did it take? How long did it take to go down?
Was it 3?
Now, how long did it take to get down there?
1 hour.
Half an hour. How long did it take to half an hour going 30 miles at 60 miles an hour is half an hour. How long did it take to get back at 30?
1 hour.
1 hour. Total time? 1.5 hours. So what is 60 divided by 1.5? And I think you were right. 40.
Okay.
Yeah, it is 40. Not 45. Do you understand the concept that you spend longer going slower, and so it has more of a contributor? It's more of a contributor to the average rate because you spend more time at it.
Yeah, when I go slower.
Okay, so little lesson here: you cannot figure average velocity by averaging the velocities. Average velocity, by definition, is distance divided by total time. Total distance divided by total time. So let's take another scenario, and let's say that you're traveling along the highway, and you have to slow down for construction, like this time of year, and you sometimes stop, and you're going to count that time as travel, and you want to find out your average speed, and you went from mile marker 125 to mile marker 223. 125 to 223, and you started the clock as soon as you hit that marker, and as soon as you hit the marker 223, you stop the clock, and that clock registered 2.3 hours.
42.6 miles per hour.
Okay.
Average.
Yes, but I want to show you the calculation, what it looks like on the board, because it should seem familiar. How do we figure total distance? How do we figure it? What did you do in your calculator to figure the total distance?
223 minus 1.
What was it? 223?
Minus 1.
223 minus 125 is how you figure total distance, mile markers, right? And how do you figure total time? With the clock. What did I say it was? 2.3 hours. So I would take the 2.3 that has elapsed minus the clock that I started at. It started at 0. Let's say we didn't use a stopwatch. Instead, let's say that you noticed right here that at the time you passed this, it was 140. And when you passed this one, it was 450.
Oh gosh. Now we've changed. Now you're going slow.
So we take 450. I know it's just a time, but that's where you landed, and you subtract the 140 where you started. Is that the same 140? Yeah. Let's make it 240 so it's not too slow.
Okay.
So I know this is clock arithmetic, and you don't want to have to. This thing right here. We could figure this out though. 4 minus 2 is 2, and the 50 minutes minus 40 minutes is an additional 10 minutes. So 2 hours and 10 minutes, right? But this is how you would figure it. You would take the time that you landed, at the 223, and subtract the time that you started at 125. Does this seem familiar at all?
This is over time.
It makes sense.
Yes.
Doesn't it kind of sort of look like this?
Oh yeah, this is one slow stop.
If you were recording on a graph distance and time, wouldn't the slope of anything on here, well, let's say it was a straight line. You just kept going. Straight line. Isn't it true that the slope would be rise which is distance, over run, which is time. This is time. This is distance. And the way we get it from this point to this point, the definition says to take this y minus this one over, this y right here minus this one over this x minus this one. It's a slope. It's a rate of change. It's an average rate of change. And so we say this in a general way. We're talking about velocity, average velocity. In general, this is a specific scenario I gave you. This is how you would figure distance. This is how you would figure total time. So we say the velocity average is going to be equal to distance to, meaning your final marker, your final point, whatever that is, minus where you started, divided by your final time minus your initial time. That's using the same subscripts I did over here. Now notice I used 1 and 1 and 2 and 2. As long as you're doing it in the same direction, we could reverse those and they both be negative, which makes it positive. It's the same number. You understand? So it doesn't really matter as long as you're doing both in the same order. In physics, they say this. Distance, position, and they use S. Final position minus initial position, they use S, it has to do with the Latin, over final time and initial time. It's all the same idea. This is just that S stands for position. This is like your mile marker post, which it gives you total distance, right? Okay, apparently I'm going too slow because I can't keep your attention, so I'm going to move on a little faster now. Example 1 says, finding average speed. So now we're not going to talk about traveling along the highway. We're going to talk about a rock falling off a cliff. I'm on page 59. You're there, okay. It says, a rock breaks loose from the top of a tall cliff. What's its average speed during the first 2 seconds of fall? Well, you got to have a formula for figuring distance for things that fall because they keep going faster and faster and faster and faster until they hit something. And so it's not like traveling at a constant 60 miles an hour or something on the road. It keeps just going faster and faster and faster. Lots and lots of study on this earth they've discovered that distance, we'll call it y because I just showed you on the graph, that's your y-axis. Distance is equal to negative because gravity pulls downward. 16 because of the mass of the earth. It's a different number on Pluto and, well, not Pluto because it's not a planet, but still it has mass.
Still a different number.
Yeah. It's different on the moon. It's different on Jupiter. This number is different here, but on the earth, on average, is 16 t squared, or t is time. And it's the squaring that causes the thing to move faster. That calculates moving faster and faster and faster and faster. Because if it were just t, it would just be linear. It wouldn't move the same speed all the time. What?
The negative because it's falling.
Yes, because it's pulling down. Because downward is talking about vectors means negative. Yes.
And how did that come out to such a clean number?
It's in feet per second. It's not so clean in metric. 4.9 meters per second and, well, actually it's 9.8.
Yeah, so how is it 16 then? Sure, that's a lot less than that.
Don't know for sure. Got lucky.
Whoa.
It probably is something different than that. That's irrational, I would imagine. Everything that's important is irrational. Anything that's natural, anyway. But it's awfully, awfully close to 16. So that's what they teach in physics. That's what we're going to go with. I suppose if you were trying to launch a rocket to Mars, they would probably use something a little more decimalized. Make sure you got the calculations right. But we're going with 16. Okay. So notice in example 1, they provide that in the solution part of the example, and then it says to find the average velocity. If this thingy right here is distance, then average velocity, based on what we just learned, should be negative 16 times 2 squared. Why 2? Because we're going from 0 to 2 seconds, right? This is your final distance figured when t is 2. Minus 16 times 0 squared. Because we started the clock on this thing falling right when it broke off. When time was 0, it wasn't moving. Well, anyway. And then on the bottom, total distance is going to be, total time is going to be 2 minus 0. Final time minus initial time. Well, this is 0. So is this. So it's going to be 4 times 16, which is negative 64 over 2.
I don't
per second squared, no, feet,
That doesn't make
sorry.
sense.
feet per second, what?
They don't have the negative in the book, I
I
guess.
know, because this
they're
guy is
going.
not a physicist and he makes me crazy. We need to be true to the physics.
That's the.
Not only does gravity pull down, so it's the velocity also indicates a downward motion. Its velocity is negative 32. It's traveling 32 feet per second. It's also traveling down, and velocity is a vector. This provides direction and this provides magnitude. The guy's nuts. He never pays attention to the physics. I'll point that out several times. Yes.
Wait, so the first second is going down at 16 feet per second, right? And then by the
Yep.
second it was doing like
32,
48?
No.
Or 64?
64.
And the average of that is 32
Because 64 and 0. We didn't average the velocities. Well, sorry. It works in this case because the initial velocity and initial time were 0. The reason it didn't work in our traveling tidal falls and back is because we had a constant speed going and coming. The beginning speed here was 0. So was the initial time. And so it does work in this case to average the velocities because one of them was 0. That's the only reason it works.
But no, but also like 6. No, that's confusing. Okay. Well,
Okay.
it's just.
That's the next question. Just hang in there.
Okay.
You're anticipating, which is great. You're anticipating, but let's go there next. Okay, so example 2 says, find the speed of the rock in the same example at exactly t equals 2 seconds. Now, he already predicted what it would be because the initial one was 0. It's going to be 64, so that the average between 0 and the final one can be 32. But that only works because the initial value was 0. So anyway, this is not the best example because of the zeroness of part of it, but this is average velocity, and what we want to do is figure out the actual instantaneous velocity. And that presents, if we're going to use this same definition that I showed you before, which is position minus position over time minus time, that presents, if we're going to try to use that definition to find an instantaneous rate of speed, provides a real problem for us. It's going to be a problem we're going to deal with all through this chapter and revisit as we go clear through the book. And that is, you can't divide by 0. If you want to find instantaneous speed, in other words, if this rock were wearing some sort of speedometer and you wanted to read it at exactly 2 seconds, and you wanted to know what that reading is, using this definition, the time elapsed at that instant of time would be 0, because it would be 2 minus 2. Can't divide by 0. Never can. Never have been able to. Never can. I never learned to, ever. In all the math that I've had more than you, and that's not to say I've had all math, but nobody's learned to divide by 0. Okay, so that provides quite a problem. And it wasn't until Newton and Leibniz, do anybody have any idea what years they were around? Isaac Newton?
1600s.
Late 1600s, early 1700s. They crossed over the century marker, I think. You can look it up if you want. I really don't know exactly. Maybe it's 17. I think it's 16. I don't know. Look it up. Somebody look it up on their phone. Just look up Sir Isaac Newton's 1727 when he died. When he died. So late 1600s, early 1700s, right?
1642 is when he was born. Okay, well, apparently I was wrong.
Okay. 1642 to 17 something. Isaac Newton. Okay. So he was doing his work in the late 1600s and into the 1700s before he died. Same with Leibniz. Leibniz was one of his contemporaries. And up until that point in the history, people didn't know for sure how to handle this. They knew they could guess. They could estimate because they could figure out, for example, how fast the thing was going at 1.9 seconds, and they could figure how fast it was going at 2.1 seconds, and it would give them a pretty good idea. Those two numbers would tell them pretty much what was going on at 2. But nobody had a way of figuring exactly what the speed was algebraically.
But I'm confused, why does it start with 2 minus 0?
Yeah,
Like, why is it 2?
End time.
Because it was 2 seconds end time minus initial time.
but
We started, the rock broke off.
Yes.
We let it elapse for 2
we're-
seconds.
But why are we making the second number 2 then?
because that's
Because at an instant, how much time has elapsed? If you wanna know how fast the rock was going at 2 seconds, exactly 2 seconds, it would be the velocity at 2 minus the velocity at 2, well, that causes a problem too, over 2 minus 2.
Wait, what?
Yeah, it's crazy.
We're finding an
It's
instant.
not velocity, sorry, distance at 2.
Well, can you use this same formula for it?
There is no other.
But to find an
What if I
average,
made
you
one?
have to
Could you just graph
have a
it?
change.
Yeah.
Right,
X equals
which was
change.
exactly what flummoxed everybody. They could guess, they could get really, really close by making calculations with a little bit of time that elapsed, a little bit. But they could never let 0 time elapse because that causes the endless pit of dividing by 0.
So do we
So they
solve
could
it?
get really, really close algebraically and arithmetically by putting numbers in that were really close to 2. But they could never figure it exactly. They never had a way of doing it exactly, yes.
What if there is a way to divide by 0?
But you come up with it, you're gonna, yeah, you'll change the world. Yeah, okay.
So can we just solve it with like, as an equation, I'm solving all the way, and so we can just, nah, this is anticipated. I'm sure we'll listen to this.
Yeah, I'm gonna show you how they finally work things out. And it has to do with the concept of a limit. I'm gonna show you, hang in there. So remember, we're trying to find instantaneous speed at exactly 2 seconds. We know it's 64 because of the zeroness. So we know what to expect, but we haven't figured it, we can't find a way to figure it out. I want you to, well, no, I'm not ready to turn the page yet. If I did this, if I let H be, H is a very, very small time, but it is some time. There's some time that has elapsed, a little bit, but it's really, really tiny. Then couldn't I find, before I do that, I want to summarize this in a general way. This is specific to this rock. Do you understand that I could say f of t2 minus f of, meaning the function value at the final time, I'll use final, minus the function value at time initial over time final minus time initial. That would do it for me. If I had a function I could plug it into. These are y values, these are x values. So it's a slope, right? This providing my plug-in, this providing my y values, my f ofs, function of time. This is a general way of figuring average speed. Velocity average. Do you understand this notation? If not, I need to talk to you about it. This is our function. We plug in t values, it kicks out y values. The difference in those y values over the difference in the x values should give me slope, which is average rate. You with me? So if I let h be a very, very, very small time, does it make sense to you that I could find really, really close to what I'm looking for if I did f of t plus h? That's a little teeny tiny bit past 2. If I let t be 2. It's a little past the time. Minus the actual time. Divided by t plus h minus t. Have I lost you?
What does that mean at H do?
H is just slightly beyond the time we're interested in.
So it just makes the two
The smallest
bigger.
unit of time.
Makes, yeah, 2.01, 2.001, 2.00000000001. H is something very small. And people always ask at this point, and I'm surprised nobody said it. You guys are holding your tongues pretty well. Well, how small? And the answer is, as small as you would like. Well, how small is that? Well, I don't know what you like. As small as you would like, so long as it is not nothing. It could be, but that's not very small. You won't get very close. The smaller h is, the closer you're going to get to the true value because the smaller the distance has elapsed. I mean, the smaller the distance, you know? Smaller the time difference,
Is that not the same as what they did, kind of the same as what they did before?
Exactly.
Really close to.
Yeah, except for we did 2 seconds and 0 seconds. They were a long ways apart because we were looking for an average. Now that we're looking for an instantaneous, we let h be very, very small, and we still take a difference in y's over a difference in x's because that's our definition. But we just make the gaps really, really tiny so long as they don't arrive at 0. And this thing simplifies to f of t plus h minus f of t over h. Remember that from your summer homework? I told you this is going to be a big part of your life.
Why can't we, give us an example of one that would end up in dividing by 0?
Yes, if you want to find the speed of this rock at exactly 2 seconds. Because if you use the definition that we have, the only one we have, you'd end up with 2 minus 2 down here. Can't have it. You can't divide by 0.
One of the costs comes out to.
It's going.
You want the speed of light.
It's going. Okay, it's going. And we need, before we found an average of the speed. Now we're finding at one point, at exactly 2 seconds, what is the speed?
But the only tool we have to use is this averaging thing.
That's all we got.
Because that's all people.
That's the only definition we've had. That's all the only definition that Newton and Leibniz had.
Why have it started?
Create another formula.
He doesn't get why it's 2 minus 2.
Yeah, why is it?
Instead of like 2 minus
So
0.
we only have 1, 2. We're only trying to find the time to add 2, so why do we have 2 2's in there?
We want the average times.
Because this is the only formula to use for average.
No, that's not what he means. That's not what he means.
I'm just trying to.
Listen, the reason why you're struggling is because this is sort of a poor example since it started at 0. These are worthless to us, and so it feels like we should be able to divide this by this. But if this has some value and this has some value, you're in trouble.
Why?
Because figuring it at exactly, let's say you wanted to find out the average speed between 4 seconds and 8 seconds.
The average speed between 4 seconds and 8.
The average speed between 4 seconds and 8 seconds would be f of 8 minus f of 4 over 8 minus 4.
You could do that.
You could. That would tell you the average speed between 4 and 8 seconds. What if you wanted to find the speed at exactly 8 seconds?
Then you would do the negative 16 of 8 squared over 8.
Minus 8.
Okay.
No,
Okay.
minus
The problem you're having is that we're thinking we start every time we're thinking we start the clock at, we start the timing at 0.
Start early.
Let's say we let the thing fall for 4 seconds, and that's where we start the clock.
Then you
Started at
just add
4,
seconds.
and yeah, and then this difference here would be 4 minus 0, where this would still be f of 8 minus f of 4, and this would be 4 minus 0. Then now you got, 4 minus, that would be trouble.
Why can't you just still just put 8? What?
It doesn't matter
where you started
the clock.
Starting the clock at a different time doesn't affect how fast it falls, does it?
It affects that, well, no, it doesn't. It affects this number right down here a little bit.
What does that number mean?
That's the difference in time. The difference in time is 2 minus 0. This is the difference in the distance that's been traveled.
Just put 8 minus 4.
We would have if this were 8 and this were 4. But if I wanted to find instantaneous speed at 8, this would have to be 8 and 8.
See, that's where he doesn't understand it. It's why the second one has to be
You're
8.
trying to find the average of that very instant, but since it's not
We're trying to find
We only have a formula for averaging, and we want to use it to find instant, and that's the problem.
So if it starts
Because
at
it causes
8 seconds,
division by 0
seconds,
right here.
How fast will we go? I don't know. Because that's 0.
Zero, because there's no
Okay.
boom problems.
Just go with me, okay, for a minute, okay? So,
Go on, say.
shh. This is the concept of limit. If we put the concept or the idea of a limit in front of this, the limit as h, that little bit of extra time past 2, if we let that limit go to 0, but not let it arrive at 0, as we let it get closer and closer and closer and closer to 0, with this gives it this whole idea, it gets us closer and closer and closer to instantaneous speed. But we can't let h arrive at 0 in this form anyway, because we get division by 0. We just can get closer and closer and closer.
So the limit's just getting closer, closer, and closer.
Yeah, that's the idea of a limit. And they say, well, how close? And you say, as close as you would like, but you may not arrive. You may not arrive at 0 or you're going down the rabbit hole.
So you're asking.
It is, same sort of concept. Yep. And this asymptotic behavior is going to be very, very important for us for setting limits. It's very good observation. Okay? Now, that's what they're showing you at the bottom of page 59. Notice they're saying the change in y over the change in t, meaning the change in distance over the change in time when h is very small is what they're showing you right there. So we would do 16 using this function right here. We would say that this one right here is f of that would be negative 16 times t plus h squared, because we're plugging this in for the t
This
value.
is just
right
if we're talking about volume.
What's that?
This is
Oh no, this is for any motion.
any.
Yep. But you have to have a function that represents it. In this case, it's a falling one, which has a square quadratic.
That's right.
Okay, yeah. Okay. Minus f of t, which is negative 16t squared, all over h. That's what we have in this particular instance because that's the function that predicts motion for this rock on Earth. That make good sense to you or not? And what we want to do is take the limit as h goes to 0 without arriving. We can't let h be go to 0 because if we did, we'd have division by 0. Does that make sense to you? We can't let it arrive there. Okay, now I'm going to erase this over here, and we're going to take a look at how we can evaluate this algebraically and numerically and maybe graphically. Turn a page. We'll try to figure out what this is. So if you'll notice the table 2.1 on page 60, right next to it right there, take a look at what they've got. They've got our equation that we have up here, our limit and our change in y over the change in t. And they have several values of h that get smaller and smaller and smaller. So the first one is 1. If you plug a 1 in for h, you get 16 times 3 squared minus 16 times 2 squared because h is 1. If you let it be 0.1, you get 65.6. So we're only letting a tenth of a second. If you let it be hundredths of a second, you get 64.16. And so forth. You keep letting it get smaller and smaller and smaller amount of time. And it looks to me like the y values over there are getting closer and closer and closer to what Sam predicted, which is 64. And it would continue to get closer and closer and closer asymptotically, like Axel observed.
So when you solve it out, you can just delete your h term, basically, and that'll give you your number.
Does it?
Yeah. Because you ended up with 64 plus 16h, so if you just got rid of the 16h.
Let me get to there with everyone first.
Let us
Okay.
arrive at the same.
So, do you understand? This is called a numerical investigation or solution. Numerical because you've got changes in h and what produced the changes in our function that we're plugging h into. That's numerical because it's a table, it's a list. Now we're going to do it algebraically. To do it algebraically, we're going to work on this part and we're going to take a look at the limit later. But right now, we cannot let h arrive at 0 because we have division by 0. So we're going to do the algebra on this. Stay with me. It's going to be negative 16, and then we're going to square that binomial, which is t squared plus 2th plus h squared. Remember foiling a binomial? Everybody clear on how I got this? Minus, or actually plus, 16t squared. You see why it's plus? Okay. All over h. Continuing, we get negative 16t squared minus 32th plus or minus 16h squared plus 16t squared. That's just distributing the 16. That's all I did. And then we start to combine like terms, and you see that these add out. And what I have left is negative 32th minus 16h squared. And if you'll remember, you can use that h under both separately because it's a monomial. Knock the h out of each, and we have negative 32t minus 16h. You understand the algebra? This thing in this rough circle here, this thing is this thing. They are equivalent to each other. They're exactly the same because we just did the algebra on it, following all the rules of algebra and simplified as much as possible. That thing right there is the same as this, which means we're really trying to take the limit as h goes to 0 of this. And now it's okay to let h arrive because we're not dividing by 0. If we let h arrive, we end up with negative 32t. And what was t? 2. Negative 64. Exactly. Not an approximation. Exactly.
We could
Yeah.
just do some simple
Well, why
algebra to
didn't
make it work. Why wouldn't it work at the beginning? Feels weird, but-
I know, because you can't divide by 0, so you have to do some simplifying. This, keep in mind, the original function, which I erased already, the original function, negative 16t squared, that's a polynomial. There is nothing more well-behaved in calculus than a polynomial. That's the reason why they're starting you out on this, because it's a fairly easy thing to have. If you've got a rational function, or a square root function, or a function, heaven forbid, which we will deal with, and doing this to it can often lead to mind-bending things. Yes?
Why can't we just create an instantaneous function, like a formula that gives you instantaneous speed?
Try and come up with it. The only thing we have to work with is an average one. If you can make that work into an instantaneous predictor, you should. You should try that. Go ahead. Nobody's been able to do it so far. Okay? Maybe. But listen, young minds that are not stuck in one way of thinking like mine can sometimes come up with great things. So don't give up, but good luck.
Can we just pass it fast if we come up with that? What, negative 16?
Sure.
Okay,
You betcha.
go say, meet me.
But do not spend all your time on that because it's likely you'll want to pass by doing the work I've done. All right. They have in here a definition of a limit. And it's one of the most arduous, difficult, unnecessary things to do. However, on your final exam in the spring, you will have to use, there will always be one problem having to do with the definition of a limit. I will teach you how to use that definition to do the problem at the end, when all this stuff will be that I'm going to teach you is all inside your head. It'll be much, much easier to understand then. And even then, it won't be easy. It's called the delta epsilon definition of a limit. Just listen to it. Assume f is defined in the neighborhood of c being an x value. So somewhere in the neighborhood of c, it's defined on that neighborhood. And let c and l be real numbers. Okay. The function f that we're looking at has a limit L on the y-axis, by the way, as x approaches c on the x-axis, if, given any positive number epsilon, there is a positive number delta, such that for all x, the distance between x and c is between 0 and delta, implies that the distance between the true value of y and L is less than epsilon. Yeah, isn't that great? It's difficult because the notation kills you. And getting the concepts in your mind is so hard. And it's so awful that the very first thing we have to give you is limits. And they give you this definition. And you're going, I'm checking out of this class, man. This is ridiculous.
I think it's too late for you actually.
Yeah. Don't check out because I'm not going to teach you this now. We'll come back to it. It's called the delta epsilon definition of a limit. And it is true, unadulterated mathematics. I'm telling you, it's hard. It can be. Okay? So instead, what we're going to do is skip that for now. And I want to talk to you about concept of a limit, not how to prove something is a particular limit. Okay, I want you to just skip over that and let's go to this. Let's see if we can figure this out. We're going to jump right to some trig. And we are going to see if we can figure out, without doing the algebra, since you don't have the skills yet. We will. No, actually, you know what? We never will figure this one out in this class. We have to accept it on faith. What I want you to think about is what is the limit as x approaches 0, not h, but x approaches 0 of sine x over x. So x is an angle. Now, obviously, we can't let x arrive at 0 or we've got division by 0 again in this rational function. But we can get really, really, really close. So what I would like you to do in your calculator, get yourself in radian mode and graph this. Don't forget that you will have an automatic parenthesis on the front of this x. You must close it before you divide by x.
Wait, so
Go to Zoom Trig after you've gotten radian mode.
what's the question?
You don't have it yet.
The question, what's the y value as x approaches as we get closer and closer to x equals 0.
Oh, and we should know this, but.
No, you shouldn't have to know that.
We should.
Because if the sign of 0 is 0, x is 0. If you let it arrive there, you got 0 over 0. You're not supposed to know what that is.
Well, I know, but like,
Well, I think it's approaching.
but we know.
You think it's approaching 1? Graph it to see. That's what I'm asking you
Well,
to
we
do.
know that sine at 0 is 0, right?
Yes.
Divided by
So
0.00.
So you have 0 over 0. Because if you let x go to 0, you've got the sign of x, the sign of 0 is 0 over x equals 0. 0 over 0 is an undefined
But
thing.
we're just trying to find the y value.
Graph the function. Graph the function and tell me what you think the value, the y value of the function is when x is 0. And you ask it, you say, what's the value of 0? It doesn't give it to you. But what is it close to?
Look at the table.
Yeah, go to your table. Remember how to adjust your table?
Plus and then intrinsic.
You go second and graph. No, you go second table set, first of all. Or you can do auto. Anyway, you go second table set and let your beginning x value be 0.01 and let your delta x be 0.001.
This is how much.
Now, go look at the table.
Oh, wait.
You don't
Not
have
so small your calculator gave up and just said, yeah.
they all appear to be
It's like,
like
no, it's
0.1.
one. I don't care if it's one.
But right at 0, we don't have a value. So this graph, actually, if you could graph it the way you'd like to, right here at 1, it appears to, I don't care what happens over here, but it appears to do something like this. It appears that there's a hole right there. But as you climb up this little mountain here, and as you get past that and go down, it's this value right here, right, really close to 0 appears to be 1. Right?
Yeah.
All right. Then the limit as x approaches 0 of sine x over x is 1. It's not really close to 1. It is 1. I need to talk to you about that. It's not close to 1. It is 1. The value of this at 0 is undefined. The value of this function at 0 is undefined. There's a hole. Your calculator doesn't know what it is. There's a hole there. But the limit, and this is where you got to get solid in your mind what the concept of limit is. And you might want to pay attention to this, Jose. The concept of limit means what value is it getting close to as this gets close to 0. And it is getting close to 1. That does not say that this function's value at 0 when x is 0 is 1. That is not what it says. It says the value that it is, the y value that this thing is approaching as we get close to 0 is 1. Do you see what I'm saying? There's a difference. Yes.
If limits don't describe what a function actually is, then why is it such a big deal?
I'll have to take that on faith for now and learn how to do it. It's extremely important.
We'll find
Okay.
out.
All right, just hang in there. At the very, very bottom of page 60, I have that limit as x approaches 0 of sine x over x equals 1. I have that in a big circle there, and this is something that you are going to want to remember because this particular expression will show up many times.
What?
You want to memorize this limit.
X equals.
Sine x over x as you approach 0 is 1.
Sure.
And we never actually did the algebra on it. It's just something you're going to take on faith based on the evidence in your calculator. Okay? Now, at the very, very bottom, the last 4 lines there, here's what it says. I want you, well, actually, as I read this, I want you to be looking at the 3 pictures at the top of page 61.
All those pictures.
Top of page 61. They all look very much alike. There's subtle differences. Listen to what I'm saying as you look at those pictures. It says, that figure that you're looking at illustrates the fact that the existence of a limit as x approaches c never depends on how the function may or may not be defined at c. This one is not defined at 0. And the limit has nothing to do with what happens at 0, only as you get close. You've got to get that solid in your mind. That's the concept of a limit. So let me read that again. The existence of a limit as x approaches a number never depends on how the function may or may not be defined there. Doesn't even have to be defined there, as this one is. The function f has limit 2 as, in this picture, the function f has a limit of 2 as x approaches 1, even though f is not defined at 1 in the first picture. The function g, the second one, the function g has limit 2 as x approaches 1, even though g of 1 is not 2. G of 1 is 1. But the limit is 2. The function h is the only one whose limit as x goes to 1 is the same as the value at x equals 1. Still, in all three cases, the limit as we approach 1 is 2, in all three cases. What actually happens at 1 is irrelevant in the question of a limit. So in the first one, what actually happens at 1 is nothing. In the next one, what happens at 1 is 1. In the next one, what happens at 1 is 2. Nevertheless, in all three cases, the limit is 2.
So a function can have a limit and the value at the same.
Yes, and they can be the same.
That's fantastic.
That's going to be our definition of continuity. If the limit and the value are the same at a point, it's continuous at that point. Otherwise, it's not.
Wow.
Okay?
It's not that different.
No, and you guys are thinking, okay, I get that, but boy, is this boring. It's be very relevant soon. Just trust me. You just have to go on faith for a little while. Okay,
You more than anyone else.
properties of limits. Properties of limits are just as you would expect. They behave properly, and that's nice. There's no surprises. So then that little tan colored box, this is what it says. You got to get in your head what's going on. First of all, they give you these two facts. The limit as x approaches c of f is L. So L is the y value that it approaches. Like in the one up there, it would be the number 2. L is the number 2. And c is the number 1. It's approaching c on the x-axis, and it gets closer and closer to 2 on the y-axis. So that's what they mean. The limit as x approaches a particular value is L. That doesn't mean it's even defined at c. There's another function, g. And we're going to approach the exact same c value, but its limit is different. It's a different y value. Okay. So then, if I sum f of x and g of x together to call it a new function, f plus g, then that function's limit will be L plus m, just like you'd expect. Difference, same thing. If we subtract f and g, or g minus f, whatever, then their limits become a subtraction, and that's the value of that new function's limit at c. Product, f times g, L times m. Constant, if you multiply a constant times one of the functions, then its limit will be that same constant times its limit, just like you'd expect. Quotient rule has a very slight stipulation, which you might expect. If you divide f by g, then that new function's limit will be L over m, so long as m is not 0. You can't divide by 0. Turn the page. If you raise one of the functions to a power, so that you have a new function of that function raised to a power, even if it's a fraction, then the limit of that function as x approaches c will be that limits raised to that same power. Okay, so it's just exactly what you expect. I really don't like example 3 because example 4 is much more illuminating. And there is one thing, though, I would like to talk about theorem 2 for just a minute, bottom page 62. Do you recognize a polynomial when you see it? Do you have an idea of polynomial in your mind? They're those things that have powers that are whole numbers but positive on the x's, and there's a whole bunch of terms like 3x to the 14th minus 2x squared plus 1, that's a polynomial. But 3x to the 2/3 is not a polynomial, right? Recognize a polynomial when you see it? Well, polynomials, we've studied those for a long time. Polynomials are always really well behaved. They either start high and end high, they start low and end low, they start high and end low, or they start low and end low, depending on the sign of their leading coefficient and the power, the leading term, power and leading term. And they never go pointy. They never are discontinuous. In other words, they never have any breaks. Polynomials are the most well-behaved functions we know. Rational functions are the next most well-behaved. Do you know what a rational function is? What does the word rational mean in math?
Fractions?
Yep. And so a rational function is a polynomial divided by a polynomial. One polynomial over another. That's a rational function. And rational functions have asymptotes. Where their denominators are 0, they have vertical ones. They have horizontal ones, depending on how the degree of the numerator compares to the degree of the denominator. You learned all these things. You may have forgotten the details, but rational functions are the next best ones. So they have a theorem about polynomial and rational functions. Here's what it says. If f of x is equal to a polynomial and c is any real number, then the limit as x approaches c is f of c. Plug it in. You want to know the limit as x approaches c of a polynomial? Plug c in, and it will tell you what the limit is. Because there's no chance that it will be undefined anywhere, that it will have a funny corner to it, or it'll be misbehaved at all. And it will cover all the real numbers. Any c you want to plug in, any c you want to find the limit of, plug it in.
Is that because polynomials are continuous?
Yes. Yes. Same thing with rational functions, so long as the bottom's polynomial at c is not 0. If it's 0, then you got problems like this. But if it isn't 0, if it's some number, then just find the first polynomial at c, the top polynomial over the bottom polynomial at c, and that fraction is the answer. So a lot of times you can, especially if you're dealing with rational functions and polynomials and rational functions, it's just a plug and chug thing. And that's what they're saying in example 4. And it's almost not worth wasting your any intelligence on this. However, it's a nice thing when it happens. So take a look. Do you understand that the function following that limit is a polynomial if you distribute x squared? You see that? Top of page 63. Are you looking there? It doesn't, in the way that it's presented, it doesn't really look like a polynomial, but if you distributed that x squared, it would be a polynomial. So if you want to find the limit as x approaches 3, plug it in. The answer is -9. The next one's a rational function. We got a polynomial that's x squared on the top and a linear polynomial at the bottom. All you have to do is figure out, if I plugged x equals 2 in, would it give me division by 0? No, it would give me 4. So plug it in, you get 3. So as long as it doesn't cause division by 4, finding a limit, by 4. As long as it doesn't cause division by 0, you can just plug it in. Causes division by 0, you got other things causing you problems like this. Okay, moving on. Look at example 5. Please don't look at the solution. Let's see if we can figure this out on our own. Okay, what we want to do now is try to find the limit as x approaches 0 of tangent x over x. That is not a direct plug-in. Why? Why can't we just plug it in?
Because you have to put 0 in the denominator. You can't
Yeah,
do that.
can't do that. You'd have 0 in the denominator, so we're going to come up with something else. Okay, do you remember any way that we could manipulate this function like we did the one that I erased over here? Any way we could manipulate this function to rewrite it in such a way that we might be able to figure the limit algebraically by direct substitution? And you're going, no, Miss J, that's what I'm here to learn. Can you think of any way to rewrite tangent? Good idea. So I have sine x over cosine x over x. I still can't take that limit. I'm going to keep the limit off until I'm done manipulating this. I'll put this over 1 to remind you of the next move. What do you suppose the next move is?
Multiply sine and cosine by 1 over x.
Invert and multiply. You're good. So it says sine x over. If I flip that over, it'll be x cosine x. Do you agree? Now here comes the inventive part, the part that may not occur to you. Don't panic if it didn't, but hopefully, you better be able to follow what I'm going to do next, even though it didn't occur to you. I'm going to rewrite this as sine x over x times 1 over cosine x. Why did I do that?
Because we know sine x over
You're allowed.
Because I know this limit. And remember, the property said, if I can find this limit and I can find this limit, I can multiply the two limits. Right? Okay. Well, this limit, so I'm bringing the limit idea back home without writing it. The idea here, that this limit is 1. So I have 1 times the limit as x approaches 0 of 1 over cosine x. Do I still have division by 0 when I plug in 0?
Yeah.
No. This is the cosine of 0. 1. What? So the limit as x approaches 0 of tangent x over x is 1. By careful manipulation, we never had to plug 0 in to have division by 0. We were able to work it out so that direct substitution did not cause division by 0. And right here, from here to here, that's the clever part. You will learn to be clever as all this stuff starts to gel in your mind again. It's not so stiff from having a summer and all spring not doing it. Well, a lot of you did it. How you doing so far? You okay? Did you follow that, I hope? Okay. Example 6. We're getting there, folks. Okay, I'll have to finish this tomorrow probably, and also give you section 2 too.
So should we do more?
You can if you want. You can get started on it if you like. Okay. The substitute will have a whole bunch of handouts for you. Like I said, they will all be due by the time I get back too, or at least you have tried everything and brought your questions back to me. You will have plenty to do. This Friday, you're going to be taking a pretest, but most of the rest of the time, you guys are on your own to work together. Do not waste the time. It's all expected to be done when I get back. I'll give you the rest of this lecture and 2-2 tomorrow, and we won't dawdle at the beginning. I'm going to have to really hustle to get through it. So, anyway, to be continued.